Okay, welcome back everyone. Today we're going to continue on with Chapter 1, Relations and Functions. We're going to Section 1.4 on function notation. Function notation is what you're probably used to seeing. Function notation is where we write the input and the output. So for example, I've got this function written as f of x equals negative x squared plus 4x plus 1. In this case, the f of x signifies that this is a function where x is the input. In other words, the x value is going to represent our domain, and then the output is whatever this equation comes out to be. We can think of lots of different inputs. For the most part in this class, unless we specify otherwise, the domain is always going to be all real numbers that we are allowed to put into the function. Sometimes we might have to restrict the domain a little bit more. We'll come back to that later. If we don't say so, the domain is always every real number that you're allowed to plug in. For this problem, it's asking us to first find this function located at a couple of different points. So we'll simply plug in. F of 2 is equal to negative 2 squared plus 4 times 2 plus 1. This gives me negative 4 plus 8 plus 1, which comes out to be 9 minus 4, 5. I do basically the same thing with f of negative 2. I'll need to make sure I'm careful that this negative 2 goes in exactly for x, which means I'm squaring this negative. And recall, when you square a negative, it turns positive. This is different than the problem we did before this, because in the last one, the negative was out front. This time, not only do I have a negative out front, but I also have one in here. The one in here gets squared away, so this becomes 4. The one out front will remain. So I have negative 4, just as I did last time. But for the next piece, because the 4 is times a negative 2, I'll basically have a minus 8 here, plus 1. Negative 12 plus 1, negative 11. Now looking at this next piece, it's a little bit weird because I'm trying to plug x's into this function that already has x's. In order to do this, simply think of this 2x to replace every single x in the original. What I like to do when you're first learning this type of process is to leave a blank everywhere that the new thing should be and just leave some empty parentheses. So that means what I'm going to have here is negative parentheses squared plus 4 parentheses plus 1. Now all we have to do is fill in the parentheses with the 2x. 2x, 2x. Now we'll probably want to simplify. So this means that since I'm squaring the 2x, both of them square. So I'll get minus 4x squared plus 8x plus 1. Nothing more for us to do. The next one, 2f of x, is different. The 2 is not plugged in, it's simply multiplied, which means all I have is 2 times this entire expression, negative x squared plus 4x plus 1. All I have to do is double. I'll have negative 2x squared plus 8x plus 2 after distribution. Let's take a look at this last piece down here. This is the kind of thing that you're going to see a lot when you move on to calculus, so we'll want to start familiar with this now. F of x plus 2 is exactly like the one we did with f of 2x. I'll be leaving myself a blank everywhere that an x would be, and then filling it in with the x plus 2. So this first step is easy. There's going to be a little bit more algebra to simplify here. I notice that at the start I'll need to FOIL, so I will have negative x squared plus 2x, and 2x makes 4x plus 4, plus here I can distribute 4x plus 8 plus 1. Then I can do, okay, so now I should distribute this negative, minus x squared minus 4x minus 4 plus 4x plus 8 plus 1. And now I can just combine like terms. Negative x squared, the 4x's cancel, and then I have 8 minus 4 is 4 plus 1, 5. Finally, let's do f of x plus 2. This one is very easy. We don't even need to get that much more space. F of x plus 2 is equal to, here's f of x plus 2. I'll just simply combine the 1 and the 2. Negative x squared plus 4x plus 3. Nothing to it. So you want to make sure that you're careful when you're doing functions. The difference between something complicated being plugged into the function and something being potentially added or subtracted or multiplied with the function. Two very different things. Now, the next thing we're going to want to do is we're going to look at further domain. Domain, if you'll recall, is the set of all x values for a function. For our functions, that's going to be everything that we're allowed to plug in. There are 3 possible restrictions for our domain. 2 of them are going to come up more urgently. There's one that we'll come back to later, but I'll list all 3 of them now. These are all 3 that we're going to deal with in this class. The first one is that when I take a root of a negative number, it has to be an odd root. Square root, for example, can't happen because 2 negatives makes a positive and 2 positives makes a positive when multiplying. So the first rule is that I can have no roots, I should say even roots, of negatives. The second rule is for division. We all know what we can't divide by. No division by 0. And the third rule is that we cannot have negative or 0 as the input of a log. We haven't talked about logs in this class, and we won't for a little bit, but we'll list this rule here just because there's only 3 rules, so not including one of them seems silly. It's the first 2, however, that we're going to focus on today. No even roots of negatives, no division by 0. So whenever you're looking at a function, what you want to say is, am I taking the even root of a negative number? Am I dividing by 0? What x values would make those things happen? In this example in this problem, for example, this root contains 8 minus 4x. That means that since this is an even root, a square root, 8 minus 4x must be greater than or equal to 0. It can be equal to 0. It just cannot be negative. And I'll solve this for x. What I would do here is I would add 4x to both sides, which gives me 8 is greater than or equal to 4x, and then dividing by 4. 2 greater than or equal to x. Now, I would like to be able to give this domain in several different forms. You might want to give it as an interval. You might want to give it in set notation. I think interval is probably going to be very helpful here. So what I'm looking for is the set of all numbers greater than or equal to 2. That means I want an interval that starts at 2 and goes on forever. So I would say that the domain is the set 2, infinity. If we were going to do set builder notation, this would look like the set of real numbers such that x is less than or equal to 2. Whoops, less than or equal to 2, not greater than. I had it backwards. That means that I actually want negative infinity to 2. You can always double check yourself so that little mistakes like this don't happen by plugging in a test value that's not equal to 2 in this instance and making sure. For example, if I had thought that it was x is greater than or equal to 2, I might think that 3 would work. But 4 times 3 is 12, and 8 minus 12 is negative, so it's not going to work. Whereas 0, which is in this correct domain, would work. 8 minus 0 is definitely a positive number. Always be sure to be careful so you don't make little mistakes like that. Another example here, but this time I have a cube root. There's no problem. So I would say that the domain is equal to R, which is all real numbers. You'll recall that for interval notation, I can simply write negative infinity to infinity in order to account for all real numbers. Because it's a cube root, I have no issues, and so every single number is a valid solution. This one here, I see 2 things that can be issues. Number 1 is the square root on top, and number 2 is the division that is inherent in the fraction. We're going to treat each of these things separately. Number 1 is the square root. I need to make sure that t minus 2 is greater than 0. In other words, greater than or equal to 0, and plus 2, this should be. In other words, t is greater than or equal to negative 2. In interval notation, this time since it is greater, negative 2 to infinity. Secondly, I need to make sure that 4t minus 4 is not equal to 0. That means that 4t is not equal to 4, and t is not equal to 1. For this one, there's a couple ways I could write it. I could say negative infinity to 1 union 1 to infinity. Or I could do r except for 1. Make sure if you do it this way that you put 1 in curly brackets, because if you're going to be removing a set from another set, you need to remove the whole set, not just a number. Sets are more compatible with other sets than they are with numbers. So removing the set makes this make more sense. So now I've got these two different pieces that define my two different domains for the two different problem points. I'll need to take the intersection of the two, because I need to make sure that any point I pick is not a problem for either. This is where it might be helpful to graph. So taking a look here, what I've got for the first one is negative 2 to infinity. And what I've got for the second one is everything except for 1. I see that my overlap is going to be this is my domain. Again, a couple ways I can describe this domain. Way number 1 that you could choose could be the intersection of union of two different intervals, negative 2 to 1, and then 1 to infinity, describing the two different pieces, 1, 2. Alternatively, you could describe this just saying I've got negative 2 to infinity, except 1. You don't include 1. Personally, I like the second one better. It shows off that what I've really got is one interval with a hole. It's not two distinct intervals. It is two intervals, but they're very closely related in that they overlap on their endpoint. So by writing it the second way, you show off that it's one interval with a piece missing. However, WebAssign will probably only take the top version, or MyOpenMath, will probably only take the top version. Therefore, I definitely make sure you're familiar with both. Let's do just one more example of this before we call it a day. Oh goodness, a fraction inside of a fraction. We'll have to be very careful with this one. First, I'm going to concentrate on the bottom fraction. Just this piece for now. The division here is 2y minus 10 cannot equal 0. We'll do some quick maths over here. And quickly obtain that y cannot be 5. For the second one, I'm concerning myself with the entire fraction. And that means that I can't be dividing where the denominator of the big fraction is 0. In other words, 1 minus 7y over 2y minus 10 cannot equal 0. Solving this equation is going to require a little bit more work than the last one. The first thing I think I'm going to do is I'm going to get this fraction by itself by subtracting 1 from both sides. You could also clear the denominator here if you would prefer, but I'm going to go ahead and finish the problem this way. Next, I am going to multiply this 2y minus 10 to both sides, which will give me negative 7y equal to negative 2y plus 10 after distributing the negative. Now I'll need to solve for y, so I'll add 2y to both sides. Give myself a little bit more space. Negative 5y is equal to 10. So y cannot be negative 2 after dividing by 5. Negative 5. I would say here, what I've got is negative 2 and 5 are my problem points. So what I would do is I would choose to write the domain as all real numbers except for those in the set containing negative 2 and 5. This is the set of numbers that I am not including. Or in terms of interval notation, you could do negative infinity up to negative 2 and negative 2 up to 5 and 5 up to infinity. Again, I like the bottom one much better. It shows off that what I'm looking at is all real numbers with 2 wholes, not 3 separate intervals, but really just one interval with 2 pieces removed. That being said, the top one is perfectly correct. It's just harder to interpret when you're new to the subject. That's all we've got for this one. I'll see you guys next time.